So here in 5.1, we're going to be talking about increasing and decreasing functions, and we're going to talk about these in terms of the derivative that we talked about in chapter 4. So a function is going to be increasing from left to right if our f of x is less than f of y, if that value x is less than y, which means if we have some point to the left, its y value is going to be less than the x values, y value to the right hand side. All right, and a function will be decreasing from left to right if that value to the left, its y value is greater than the y value of the point to the right. And visually what this looks like is we have a line that's going to be going up from left to right if a function is increasing, and a line that's going down from left to right if a function is decreasing. And when we have the derivatives, we can go ahead and easily find these intervals where these functions are increasing and decreasing because of the slope of our tangent line. So if the slope of our tangent line is positive, then our function is increasing in that area. If our slope is negative, then the function is decreasing, and that can be shown by our tangent lines. Another thing we can also find our extrema, either our minimum or maximum values of our function by using derivatives. Our slope at our tangent line at these minimum and max values are going to be 0. It's going to be a horizontal line or a line parallel with the x-axis. And so when we go ahead and take the derivative of our function, we can go ahead and set that derivative equal to 0, go ahead and solve for x or whatever variable we have, and we would be able to find the values of our minimum and maximum. It is also possible that our derivative could be undefined at our maximum or minimum values. So when we go ahead and look at a graph like this, like a absolute value graph, or some sort of graph that curves up, has a sharp point, and curves back down, the x values where that derivative is 0 or undefined will be our critical numbers. So either over at our minimum and maximum, or where we find that we are undefined, where all of a sudden at that point our derivative does not exist. These are called our critical numbers. So what we want to go ahead and do when we're looking at these critical numbers is we want to find the intervals of our function where it is either increasing or decreasing. Let's go ahead and look at an example. So here we have an example of a quadratic function in the HK format that you may have seen in college algebra. And this is a parabolic function where we have a vertex of 1, -3. As we could tell from the actual function. So this is a parabola that goes down, has a lowest point at 1, -3, and then goes back up. So this function around the vertex is going to be increasing from our 1 value all the way to infinity, but not inclusive, because at 1 we have that horizontal line. Okay, we have that minimum. And it's going to be decreasing from -infinity all the way to that x value of 1. So our increasing and decreasing values are based off of our x values. If we went ahead and had a function that was a cubic instead, so maybe this was a cubic function instead of a quadratic, we want to go ahead and find where we're increasing and decreasing. So a very similar type of function. It's in the same format here. But this is only telling part of the story. All right, so if we go ahead and graph this graph in Desmos, which I did for you on the PDF, we see that we have the graph is increasing all the way up from -infinity to 0, because here we have a maximum. And it's also increasing from 2 to +infinity. And this is where it's increasing by our x values. And then we have one area where it's decreasing, and it's decreasing in between those two values from 0 to 2. All right, and that's where we go ahead and our tangent line is negative. All right, so let's go ahead and find the critical numbers. We want to find the open intervals where f of x is increasing, where it is decreasing of this function. So we have f of x is equal to 2 3/10 plus 3 4/10 x minus 1 2/10 x squared. All right, so we want to find the critical number first. So what we want to do is we want to go ahead and set it equal to 0 and solve. Okay, and so when we go ahead and set this equal to 0, first of all, we got to find the derivative of this function, because that is how we were told to do it. So we go ahead and take the derivative. We have 3 4/10 minus 2 4/10 x, and we're going to set that equal to 0. Go ahead and solve for x, and we end up with a fraction 17/12. All right. So remember, we can't leave it in decimal form. We want to go ahead, make them whole numbers, and then go ahead and simplify the fraction. Okay. So this one here, we always have a value of 17/12. So the derivative is always defined because it's still a polynomial. We don't have any problems with the denominator where it's going to cause us to have any asymptotes. We want to find where f of x is increasing or decreasing without graphing. So what we want to do is we want to go ahead and put our critical numbers on number line to test. All right. And our critical number here is going to be 17/12. All right, because this is the only critical number we came up with on this quadratic function. And we know there should only be one turning point, because we also know that any quadratic function is a parabola. It only has one turning point. All right. So what we want to go ahead and do is we want to test some number at 17/12. And we want to go ahead and see where it's increasing. And now this is a parabola that faces downward, and so it has a highest point at the vertex. So it's going to be increasing from -infinity up to our critical number value of 17/12. It's going to be decreasing from 17/12 to positive infinity. So here what we want to do is an example of a number line check. So here's our derivative, and our critical number is 17/12. And what we want to do is we want to go ahead and plug in values close to 17/12, and we want to see what the value is. And so when we go ahead and plug in 0, we get a positive number, which means it's increasing. And when we go ahead and plug in 2, we get a negative value, which means it's decreasing. You could also graph this, but like I said, you want to be able to do this also without being able to graph the function. Okay, and so therefore we have our open interval 17/12 to positive infinity, where it is going ahead and decreasing. All right. Here we want to go ahead with number 4, find our critical numbers, open intervals of increasing and decreasing, and here we have a cubic function. All right, so this cubic function will have a maximum of 2 terms. And we have 4x cubed minus 15x squared minus 72x plus 5. We want to go ahead and take the derivative of that function first, which is 12x squared minus 30x minus 72. And this is a polynomial, so this is going to be defined. And we're also now probably going to have 2 critical points. So if we go ahead and set the derivative equal to 0, we can go ahead and pull out a whole number 6, a GCF. And this will make the function a little easier to deal with. You could either go ahead and try to factor this, or you could go ahead and use the quadratic formula for it. All right. And this one actually factors really nicely into 2x plus 3 and x minus 4. Now this 6 is not going to be a part of any of this. It has nothing to do with finding our critical numbers. And so we're really looking at the 2 factors of 2x plus 3 is equal to 0, or x minus 4 is equal to 0. So our critical numbers here is going to be -3/2 and 4. So we have 2 critical values, which makes sense because this is a cubic function. It has 2 terms. If we go ahead and plot this on the number line, we're going to go ahead and put our -3/2 and our 4. And what we're going to do is we're going to have 3 intervals where we're testing. We're going to test numbers less than -3/2. We're going to test a number between -3/2 and 4, and then we're going to test a number greater than 4. And I always recommend testing whole numbers whenever possible. It's much easier to deal with. Okay. when we go ahead and plug in these values and we have x is equal to -2, what we do is when we plug them into here, we end up with a negative value multiplied by a negative value, which gives us our positive value. Okay, so at -2, we have a positive value. This is going to be increasing. When we go ahead and plug in 0 here, we're going to end up with a negative value here. So this is going to be negative. When we plug in 0 here, this is going to be positive. So we're going to end up overall with a negative value. When we go ahead and plug in 5, again, we're going to end up with 2 negative values, which is going to give us a positive overall for our derivative. So our intervals of increasing are going to be from -infinity over on this side all the way up to 3/2 because we have a positive on our number line. And we're also going to be increasing from 4 all the way to positive infinity because, again, we tested and we got a positive value. And it's going to be decreasing in between these two values where we got our negative. So between -3/2 and 4, our function is going to be decreasing. And if you were to go ahead and graph this, you would be able to see this very clearly. Example 5 I have here, we want to find critical numbers, open intervals of increasing and decreasing. And we have a y value. Here's a linear function. Y is equal to -3x plus 6. But when we go ahead and take the derivative, we end up with just a number which is -3. Okay, so this number is always negative. Since we cannot set the derivative equal to 0, there are no critical numbers. So the function is never increasing. And because it is negative, it is decreasing from -infinity to positive infinity. Okay. If we look at number 6 here we go ahead, we have a rational expression where x cannot be equal to -1, and therefore we have a vertical asymptote at that function. So here we have to go ahead and use the quotient rule. So when we go ahead and take the derivative using the quotient rule, we go ahead and we end up with -1 over x plus 1 quantity squared, and we want to set that equal to 0. All right. When we go ahead and solve, we go ahead and multiply by this denominator x plus 1 squared, and we end up with -1 is not equal to 0 because anything multiplied by 0 is itself. So here we have no points where the derivative is equal to 0. So therefore, this function here at -1 is also undefined, and it's also not a critical number because x in the original function could not be equal to -1. So it is not a critical number. Okay, so this value here at -1 is just a vertical asymptote. And here we want to test for increasing and decreasing. And even though it's not a critical number, because it's an asymptote, we have to go ahead and test around this number to see what's happening. Okay, so when we go ahead and test this value at -1, we see that when we plug it in, we end up with negative values to the left and negative values to the right. And this is a little sketch of what the graph looks like. All right, and it's a version of 1 over x, which is something that you saw in college algebra. So this function is never ever increasing. There's no positive values, and it's going to be decreasing around the asymptote. We cannot count the asymptote here. So the values of decreasing is -infinity to -1. We have to separate it with a parenthesis, resume at -1 on the right-hand side to positive infinity. All right, and this should make sense just from the graph here. Let's go ahead and quickly look at an application. And here we have a cost function given by x cubed minus 2x squared plus 8x plus 50. And we again want to find the values where it is increasing and decreasing. And let's go ahead and take the derivative first. So when we go ahead and take the derivative, we have 3x squared minus 4x plus 8. This does not factor, so therefore we want to use the quadratic formula, and it is always an option if you want to factor or not. When we go ahead and plug that in, we end up with no intercepts. See, the graph is up here above the x-axis. So it is never decreasing since the derivative is always positive. and it is increasing from negative infinity to positive infinity. So no matter what kind of costs we are always dealing with, we're always increasing no matter how many items are manufactured.